Beneath continents ground down like old teeth and oceans laid over with new glassy floors, time keeps its quiet industry. Cities become powder, highways turn to clay. The soft pulse of electricity ends, absorbed by basalt and bone. Yet the planet remembers in other languages, in isotopic size of carbon and nitrogen, in thin, dark laminations where oceans forgot to breathe, in the glitter of new alloys and the ghost of polymers that learned how not to die. The rock record is a choir with missing voices, a ledger with most of its pages burned, and still it speaks. Across this mute archive arises a question with the gravity of myth and the austerity of physics. What if intelligence did not arrive once, but again, and again, like a fever the planet can catch? If an industrial civilization had bloomed in some forgotten age, would the crust confess? Or would the story hide inside the noise of natural cataclysms, volcanic exhalations, methane upheavals, carbon spirals, that look so much like us that the two are indistinguishable? This is not a tale of ruins found. It is a hunt for signatures that cannot lie, for altered ratios in ancient shells, for metal peaks in mud, for synthetic molecules that do not belong to any season of the Earth. It is a patient, unsettling inquiry, paced by drills and mass spectrometers, by orbital sensors and the stubborn logic of thermodynamics. It invites humility, that humanity may be singular in culture and precious in memory, yet not unique in category. The planet endures experiments. Whether it conducted one before remains the most delicate question a stone can answer. On a winter page of the scientific record, a question was written with the restraint of a ledger entry and the daring of myth. In 2018, climate scientist Gavin A. Schmidt of NASA's Goddard Institute for Space Studies and astrophysicist Adam Frank of the University of Rochester posed it plainly, not whether a prior industrial civilization did exist on Earth, but whether geology could ever prove or disprove that it had. The proposal was published in the language of astrobiology, where worlds are read like slow-burning books and where the smallest page, 1 centimeter of mud, can hold the fate of 1,000 years. Their thought experiment did not summon lost cities or dragons from the strata. It asked something harder: what does industry look like when pressed into stone? The question rose from an era learning, sometimes reluctantly, to see itself. In the late 20th and early 21st centuries, researchers began assembling the Anthropocene fingerprint, a global palimpsest of human activity etched into air, water, and sediment. The signal arrived in many dialects. There were plastics, polymers that drifted across ocean gyres, powdered into micro and nanoparticles, sank with marine snow, and fused with beach gravels into a strange hybrid called plastiglomerate. There were concretes and ceramics, new mineral-like phases born in kilns and poured in astonishing volumes, their crushed dust already sifting into floodplains and quarries. There were radionuclides, isotopic scars from mid-20th century weapons testing, cesium, plutonium, americium, brief-lived in human terms, yet precise as clock hands for stratigraphers. There were spheroidal carbonaceous particles and fly ash microbeads from combustion, metallic peaks, and altered metal ratios from mining and smelting, and a rewritten nitrogen cycle traced by shifts in delta N, the quiet outcome of Haber, Bosch chemistry feeding billions. Each arrival was both artifact and process, an industrial echo that could, in principle, harden into a geological archive. Schmidt and Frank held up this modern mirror to the deep past and asked, if today is legible, might something like today be legible at 10 million, 50 million, or 100 million years remove? The Silurian Hypothesis, named with a wry nod to a science fiction idea of primordial reptilian intelligences, but anchored in sober method, was offered as calibration. Before telescopes can diagnose pollution in the atmospheres of distant exoplanets, planetary scientists must understand which signatures of technology survive on a world like this one, and how they can be disentangled from nature's own high drama. The Earth, in this framing, becomes a testbed for reading technosignatures, a planetary Rosetta Stone that can be used to avoid false certainty when gazing outward. Geology has seen upheavals large enough to rival the Anthropocene's force, and these natural events supplied both inspiration and warning. Around 56 million years ago, during the Paleocene, Eocene thermal maximum, the PETM, carbon isotopes veered sharply negative, a fingerprint of a massive and rapid carbon injection into the Earth system. Global temperatures rose by several degrees, the carbonate compensation depth shoaled as seawater acidified, and carbonate shells dissolved on the seafloor. Polar regions warmed intensely, forests shifted, dwarfing among mammals and turnover among foraminifera whispered of planetary stress. In the muds and clays, the Delta 3C excursion sits like a sudden breath held too long. Volcanic outgassing from a large igneous province, the destabilization of methane hydrates, oxidation of organic-rich sediments, each has been argued as cause. The signal, though ancient, is startlingly familiar. A rapid carbon pulse, an ocean that forgets how to buffer, a climate that sprints. The PETM was not alone. In its wake came smaller Eocene hypothermals, rhythmic echoes, each marked by carbon isotope perturbations and sediment changes, reminders that the climate system can flicker. Farther back, in the Cretaceous, oceanic anoxic events painted the stratigraphic record with black shales, intervals when vast tracts of seafloor went oxygen poor, organic matter accumulated, and the chemistry of the oceans reset. Mercury anomalies tied to volcanism thread through some of these sequences. The breadth of large igneous provinces can be measured in metal and soot. The planet, unassisted by any industry, has repeatedly pushed itself into states that resemble, at first glance, an Anthropocene gone to seed. Warming, deoxygenation, altered biogeochemical cycles, a rearranged carbon ledger. These episodes are the essential, false positives that any claim of ancient industry must overcome. In the language of instruments, they are the background signal, the cosmic noise against which a faint, technological melody would have to be heard. If plastics or their altered residues are absent, if metals align with volcanic fingerprints, if isotope shifts match known natural patterns, the hypothesis becomes a lesson in humility. Nature, too, can draw the same curves on a graph. But the mirror does not only warn, it instructs. The Anthropocene fingerprint, as it is painstakingly catalogued, offers a palette of features whose combination may be uniquely industrial. Synthetic polymers are not just hydrocarbons, they arrive with specific additive chemistries, phthalates, flame retardants, stabilizers, that might, under burial and diagenesis, yield rare molecular fossils. The nitrogen cycle's industrial rewrite is not merely an increase of fixed nitrogen. It produces spatial and temporal delta-N structures linked to synthetic fertilizer use and wastewater discharge, potentially leaving a patterned residue in lakes and continental margins. Metals from mining and smelting do not simply spike. They alter ratios, scatter across basins, and sometimes deposit as spheroids or novel phases. Even if radionuclides decay, their daughter products, defect tracks, or anomalous distributions of stable isotopes might linger as ghostly clues. The question is not whether any single marker could be natural, but whether a suite of markers could align in a way nature rarely does. The thought experiment, then, is not a myth hunt but an audit. It asks how a civilization's metabolism, its energy sources, its chemistry, its waste, could leave a coherent global stratigraphic signature that remains distinguishable after the ravages of time. It acknowledges geology's cruelty to surface memory. Tectonic plates recycle crust, erosion erases, unconformities stitch centuries to seconds. Most of the planet's surface rocks are young. Most of its deep-time surfaces have been planed away. Cities prized by archaeologists, built of wood, steel, glass, are tender things compared to the patient violence of uplift and rain. In tens of millions of years, artifacts crumble into particles, and particles blur into geochemical averages. The convergence of a climate modeler and an astrophysicist made the question both more precise and more ambitious. Climate records, ice cores for the recent past, sediment cores for deeper time, are dense with spikes and excursions, some understood, some not. Astrobiology, meanwhile, stands on the edge of a great observational bloom, with telescopes ready to pull spectra from exoplanet atmospheres and to search for gases out of chemical equilibrium or aerosols unlikely to be natural. To move from wonder to inference, it needs ground truth, a catalogue of which planetary gestures belong to volcanism, biology, weathering, or to technology. Earth, read backwards, is the training set. The Silurian Hypothesis reframed planetary history as a series of testable signatures rather than a museum of lost artifacts. It brought the search out of caves and into core repositories, out of legend and into mass spectrometers. It suggested that the deepest traces of intelligence are not statues, but cycles. Carbon slowed or sped, nitrogen curved into new paths, metals scattered in ratios that betray smelters rather than volcanoes, polymers rephrased by heat into stubborn, unfamiliar residues. It proposed a discipline that might be called planetary archaeology, in which the tools are not trowels, but isotope ratios, and the ruins are not walls, but paired anomalies across oceans far apart in space and once close in time. In this reframing, the PETM and the anoxic events are not distractions, they are calibrations. They show the drama nature can author without help. They constrain the null hypothesis, giving shape to the argument that any industrial claim must exceed. If a prior civilization existed and burned carbon in quantities rivaling modernity, its mark would need to sit atop the planet's own volatility, distinguished by a braid of signals rarely found together. If it used energy in different ways, geothermal or solar, in such a form as to leave little geochemical wake, the archive might be thin, a whisper beneath a storm. Either outcome is instructive. The first sharpens the eyes, the second warns of ephemerality. Through this lens, the 20th century bomb peak becomes more than a historical footnote. It is a stratigraphic test signal, checking how quickly fine layers capture and mix a global event. Microplastics, once lamented as pollutants, double as traces of transport and burial. Spheroidal fly ash, dismissed as industrial dandruff, becomes a clock for the age of combustion. Each modern mark is a controlled experiment in legibility, an accidental gift to those who will read the rocks long after present memory is lost. Thus the hypothesis stands not as a claim, but as an instrument. Its provocation is disciplined. It asks researchers to assemble libraries of false positives and to develop discriminants powerful enough to separate a volcanic carbon pulse from an industrial one, a natural metal bloom from a mined one, a biogenic organohalogen from a synthetic cousin. It requests cross-basin synchrony checks, the use of mercury as a proxy for volcanism, the search for additive-derived molecular fossils, the mapping of delta N anomalies where rivers met coasts under fertilizer rain. It urges an accounting of preservation biases and a patience with absence. In the calm cadence of geology, where a million years is an easy step, this discovery phase is not a revelation, but a reorientation. Intelligence, seen this way, is a kind of geochemistry that briefly accelerates. The earliest task is to learn how acceleration appears in stone, how it differs from nature's own rushes. The climate scientist brought the stratigraphic lenses, the astrophysicist brought the exoplanet horizon. Between them, a method took shape, a way to ask the Earth a question it has never been asked so carefully. Whether the answer is silence or confession, the script for listening is now on the table. The first jolt arrives not from a trench or a trowel, but from a microscope and a mass spectrometer. Archaeology, practiced in sunlit holes and careful brushes, expects the hard angles of intention, walls, tools, scripts on clay. Geology, which works in dim laboratories and on windswept escarpments, preserves something else, processes. It keeps the memory of how seas breathed, how continents eroded, how volcanoes exhaled. When the question of ancient industry is turned toward deep time, the stage lights shift from plazas to pelagic mud, from broken amphorae to broken isotopes. Evidence, in this reframed theater, is no longer a statue in situ. It is a ratio that should not be where it is, a polymer residue that learned to endure, a feathering of metals in sediments whose pattern does not match any furnace the Earth runs by herself. This is the paradigm tension at the heart of the Silurian hypothesis. If an industrial civilization once existed far back in the ledger, its most durable legacy would not be monuments. It would be edits to cycles, carbon bent out of its slow arc, nitrogen forced through new gates, metals scattered in ways volcanoes rarely manage, synthetic molecules laid into strata that do not know the scent of phenols or phthalates by any natural route. Where archaeology seeks a shard, stratigraphy seeks a signature. The shock is emotional before it is technical, intelligence reimagined as geochemistry. Against that reimagining stands the tyranny of time. Planetary memory is not a library, it is a recycling plant. Oceanic crust, born luminous at mid-ocean ridges, slides back into the mantle in less than 250 million years. Most of the seafloor younger than the dinosaurs, none older than that survives to tell an older story. Continents keep their bones longer, but even there, rain is patient and rivers are tireless. Uplift exposes, frost fractures, roots pry, gravity persuades. Unconformities, gaps in the record where layers are missing and eras collapse into a single line, run like erased sentences through stone. 1,000,000 years of weather can reduce a city to a rumor and then to an average, until what remains is not architecture but chemistry. The scale itself distorts intuition. A centimeter of fine-grained marine sediment can condense centuries. A layer the thickness of a finger might archive the rise and fall of empires, the coming and going of fuels, and leave behind, after diagenesis, only a darkening, a shift in carbon's handwriting, a dusting of unfamiliar spheres. In floodplains and deltas, those frantic notebooks of the surface, sediments migrate, are reworked, mixed, and shuttled to the shelf. Even the most extravagant industrial age becomes, under this arithmetic, a statistical whisper in a basin's long conversation with gravity. Preservation is biased, and the biases are cruel to artifacts. A steel beam is only iron in denial. Oxygen persuades it back. Glass devitrifies, concrete hydrates and fractures, copper finds sulfur and becomes another mineral. Plastics splinter under light, heat, and time until only fragments and then molecules remain. What endures most reliably is not the object, but the externalized effects of making it: soot, altered nutrient cycles, the redistributed periodic table. Modern stratigraphers, in debating how to name and mark the Anthropocene, have assembled a grim and precise inventory of what lingers. Spheroidal carbonaceous particles from high-temperature combustion, fly ash microbeads that carry the signature of power plants, nitrogen isotope patterns in lakes and margins bent by ammonia and nitrate once made at industrial scale, radionuclides that arrived in the early atomic years and settled like invisible dust. Microplastics and plastiglomerates fused into beach rocks by heat and waves. Each of these markers confirms the same lesson: geologic memory keeps the fingerprints of processes better than it keeps the hands. The second jolt is epistemic. Natural history already contains scenes that resemble the silhouette of industry. 56 million years ago, the planet flared into the Paleocene-Eocene thermal maximum. Carbon isotopes swung negative in a sharp excursion, testimony to a rapid injection of isotopically light carbon. The carbon at compensation depth shoaled, and shells on the abyssal plains dissolved into hazes. Temperatures climbed across latitudes, hydrological cycles intensified. Forests migrated, mammals shrank and radiated, and the oceans tilted toward breathlessness. In the record, the PTM looks like a controlled experiment in planetary warming without industry. A carbon surge, a fever, a recovery measured in tens of millennia. Whether driven by volcanism, methane from hydrates, oxidation of organic-rich sediments, or some conspiracy among them, it stands as a warning that the Earth can write unaided, a curve that looks confoundingly familiar. There are other lookalikes. In the Cretaceous, oceanic anoxic events painted the stratigraphy with black shales, intervals when seas lost oxygen over vast domains, organic matter buried itself fast enough to escape decay, and trace metals like molybdenum and uranium enriched sediments in telltale ways. Mercury anomalies thread through some of these chapters, pointing to volcanic breath as a proximate driver. Large igneous provinces, the Deccan Traps, the Siberian Traps, others less famous but no less forceful, have released enough gases to renovate climate, chemistry, and life. Their signatures can include metal spikes, soot, and carbon isotope swings. These are nature's forged passports, the false positives that any claim of ancient technology must be able to read past. To say that the planet can imitate industry is not to declare the search hopeless. It is to declare what kind of subtlety is required. A volcanic pulse of carbon is not identical to a coal-fired one when examined with enough lenses at once. Hypotheses break not under single measurements, but under combinations. A negative excursion in Delta 3C can be natural. Pair it with a contemporaneous, globally coherent shift in Delta N, consistent with synthetic nitrogen flooding watersheds, and the probability space begins to reshape. Mercury, as a volcanism proxy, can help assign culpability to magmas. Organohalogens, molecules rare in biogenic pathways but common in manufacturing, could, if preserved as altered residues, tilt the scale. Metal enrichments must be read not only by abundance, but by ratios and spatial patterns. A mining and smelting footprint spreads differently from ashfall or hydrothermal vents. Even decayed radionuclides can leave daughter distributions and lattice defects that serve as time ghosts if resolution is high and context is secure. Still, the timescale terror remains the central difficulty. Consider the staging of the archive. Fine laminations form where the water column grows quiet and oxygen leaves the bottom, fjords, restricted basins, some continental margins, allowing seasonal or even annual layers to stack without interruption. These are the pages on which a brief industrial chapter might be legible in tight script. But such basins are local. Synchrony across basins is required to claim a global imprint. Elsewhere, waves and burrows, storms and worms reincorporate signals into a blended fabric. Biotubation does to sediments what crowds do to whispers. There is also the matter of representativeness. Urban and industrial landscapes tend to grow on coasts and rivers, precisely the places that travel. Their sediments are rich but noisy, their archives detailed but parochial. A global hypothesis needs global consonance. The planet answers in choir, not in solo. Matching patterns across distant basins, simultaneous isotope moves, coordinated metal behavior, the same family of molecular fossils, would be required to conjure the outline of a civilization from a lithified fog. The intellectual shock extends to the meaning of artifact. A polymer fragment in a Miocene clay is by itself only an enigma. A suite of additive-derived molecules appearing in the same interval in Africa and in the North Atlantic, coupled with altered nitrogen cycling and non-volcanic metals, would be a different category of claim. A glass shard is not necessary. A coherent anomaly is. The evidentiary grammar changes from nouns to verbs, from objects to actions recorded in matter. There is humility in the calibration itself. Even for the present, the attempt to canonize a formal stratigraphic boundary for human influence has encountered debate. What marker, which section, how global, how synchronous? If naming now is difficult, decoding then is a harder art. The lesson is not paralysis, but precision. Sensible priors demand that natural explanations be exhausted with rigor before any industrial inference stands. Volcanism is a prolific culprit. Methane clathrates wait quiet and powerful. Orbital forcing paces ice and heat. Biology can create and erase oxygen with shocking agency. The burden of proof is not rhetorical. It is multi-proxy and global. And yet the possibility that technology can be seen as a planetary process leaves a durable insight. Intelligence, viewed through this lens, is a brief acceleration in the cycles rocks remember. It mines buried reductions and releases them as gases. It rearranges elements. It invents molecules unknown to ecologies and tosses them into air and sea. That acceleration may be violent enough to leave an unmistakable seam, or careful enough to pass almost as a natural tremor. To ask which it is, in some buried chapter, is to treat minds as phenomena among phenomena, subject to the same patience of testing as any other force. The shock resolves into a method. Search not for lost avenues, but for abnormal synchronies. Favor basins that bind fine time. Use mercury to filter volcanic noise, nitrogen isotopes to track fertilizers, carbon isotopes to watch the global breath, trace metals to map industrial fingerprints, and organic geochemistry to listen for ghosted synthetics. Except that absence of technofossils is not dispositive, that erosion is loud, that subduction is final. Demand, above all, a pattern too contrived for volcanoes, too coordinated for weathering, too quick and planetary for biology alone. In that method, all remains. The Earth's archive is damaged, but it is not mute. Cities will continue to become statistics, monuments will continue to become clay, but a civilization is not only what it builds, it is what it does to cycles. If anything like industry ever rose and fell when reptiles ruled or when mammals were new, its truest monument would be written where archaeology seldom looks. Thin and dark, quiet and global. The the record of a planet briefly taught to move faster than it prefers. The investigation begins with a library, not of books, but of signals. In drawers where cores lie like sliced time, researchers assemble a lexicon of markers that an industrial age impresses upon a planet. Each entry is a quiet insistence that processes endure long after artifacts fail. Together, these entries outline a fingerprint that could, in principle, fossilize. First among them is carbon's altered voice. The isotope ratio delta 3C, the balance between heavy and light carbon, can lurch negative when vast quantities of isotopically light carbon flood the system. In the modern era, that flood is tied to the oxidation of fossil fuels, ancient photosynthesis burned back to breath. In strata, such a pulse would appear as a sharp excursion toward lighter values, but the excursion alone would not suffice. Investigators look for co-markers, simultaneous shoaling of the carbon at compensation depth as acidic waters dissolve seafloor carbonate, a spike in weathering traces as intensified hydrology scours continents, a sedimentological shift toward finer, darker layers where oxygen retreats. Carbon, asked the right questions, describes not only that something changed, but how quickly and in what company. A second entry tracks nitrogen's redirected paths. Agriculture on a planetary scale reworks the nitrogen cycle, fixing atmospheric N2 into ammonia, nitrate, and urea that cascade through soils, rivers, and seas. In sediments, this intervention can imprint shifts in delta N, signatures of changing source mixtures and microbial processing. Coastal margins may record enriched values where wastewater and denitrification dominate. Lakes and shelves may preserve lowered values where fertilizer and increased productivity alter the balance of fixation and loss. The pattern matters more than any single number. A persistent, globally coherent reshaping of delta N through time would mark an era that taught nitrogen to run faster than biology alone prefers. Technofossils form a third, more literal shelf in the library. Plastics, concretes, synthetic fibers, and novel mineral phases are not merely objects, they are potential stratigraphic characters. Concrete and clinker leave alkaline, calcium-rich residues and microstructures unfamiliar to natural cements. Synthetic textiles shed polymer threads that settle with dust and diatoms. Plastics, with their multitude of backbones, polyethylene, polypropylene, polystyrene, PET, PVC, fracture into smaller and smaller pieces, then sink in fluff and marine snow, becoming constituents of muds and sands. On beaches, wave energy and fire can weld them into rock-like fusions, plastiglomerates, hybrids of polymer and lava, shell, or sand that behave like stones and can be buried as such. Under heat and pressure, many polymers decompose, but not into oblivion. Residues can carbonize into cross-linked, kerogen-like material. Additives can leave molecular ghosts, aromatic fragments. Plasticizers turn to altered compounds, potentially recognizable by their structures even when the parent chain is lost. Fluoropolymers and other highly stable chemistries add another possibility, halogen-bearing signatures that biology does not commonly write at scale. Over geologic time, the best that might survive is not a bottle, but a pattern of unusual organic molecules entombed within otherwise ordinary shales. A fourth family gathers the metals. Industry redistributes the periodic table, lifting elements from concentrated ores and scattering them as dust, waste, and alloy. Aluminum, once rare as a native metal, becomes ubiquitous in clays and tailings when smelters operate. Copper and chromium mingle in ratios that do not match volcanic aerosols or riverine supply. Platinum group elements ride catalytic converters and enter roadside soils and sediments as subtle enrichments. Rare earths, leveraged in magnets and screens, can alter normalized patterns in ash and estuarine mud, leaving anomalies that differ from those tied to phosphates or igneous sources. Spheroidal fly ash particles, cenospheres and plerospheres born in high-temperature combustion, drift and settle as glassy bubbles rich in iron and aluminosilicates, resilient enough to endure burial and diagenesis. Read together, these metals recount an elemental diaspora unlikely under purely natural dispersal. Within this library, plastics deserve a longer reading. Their afterlives are complicated, contingent on environment and chemistry. In sunlit waters, ultraviolet radiation and mechanical abrasion embrittle chains, biofilms coat surfaces and change buoyancy, Fragments fall through the water column attached to fecal pellets and sinking aggregates. On the seabed, burial slows further degradation, and anoxic conditions can favor preservation of complex organic matter. In coastal zones, heat from wildfires and campfires welds polymer to beach sediment, producing plastiglomerates that behave like clasts, subject to the same transport and burial as pebbles. Within the subsurface, rising temperatures and pressures rewrite polymer backbones, expelling volatiles and leaving carbon-rich residues. Polyvinyl chloride, with chlorine in its chain, can dehydrochlorinate, leaving conjugated residues and releasing HCl that interacts with surrounding minerals. Polyesters can hydrolyze, polystyrene can shed aromatic fragments, polyethylene and polypropylene, once reduced to waxes and oligomers, can participate in the long alchemy of kerogen formation. Additives, phthalates, brominated flame retardants, UV stabilizers may transform but not vanish, lodging themselves as altered diagnostic compounds. After millions of years, what remains might be ambiguous: an organic signal with odd distributions of functional groups, halogens where biology rarely places them, and compound classes that hint at manufacture. The residue would not look like a shopping bag. It would look like an enigma, one best interpreted with context from other markers. To separate industry from nature in deep time, researchers study the planet's own sudden fevers as training sets. The Paleocene-Eocene thermal maximum provides a canonical case. Its portrait includes a prominent negative delta 3C excursion recorded in both marine and terrestrial archives, a global temperature increase of several degrees, and evidence that the carbonate compensation depth rose toward shallower waters as the ocean acidified. In the cores, a dissolution horizon, where carbonate shells thin and vanish, can be traced. Mercury enrichments, often used as proxies for volcanic emissions, appear in some sequences and help connect the event to contemporaneous magmatism. Laminated, finely bedded sediments in certain basins carry the signal with seasonal or annual resolution, allowing estimates of the event's onset rate. Whether the carbon pulse unfolded over millennia or centuries is more than an academic point, because industrial scenarios would write far faster. Other hypothermals in the early Eocene, the smaller echoes that followed the PTM, offer additional templates. By coupling delta 3C records with carbonate saturation changes, mercury anomalies, and sedimentary structures, investigators constrain the relative roles of volcanic outgassing, methane release, and organic matter oxidation. The logic is comparative. Volcanism carries with it mercury and sulfur, altered strontium isotopes in seawater due to enhanced weathering, and a suite of trace metals in patterns tied to ash and aerosols. Clathrate destabilization, releasing methane-rich in light carbon, might drive a sharp delta 3C drop without the mercury signal of lavas and with a distinctive duration and recovery trajectory. The oxidation of large terrestrial carbon reservoirs can leave its own fingerprints in plant wax isotopes and terrestrial sedimentation rates. A hypothetical industrial spike would need to be considered against these known families. It would likely be rapid in onset, globally synchronous, and accompanied by signals alien to igneous or microbial agency, additive-derived organics, metal ratios suggesting mining and smelting, and nitrogen cycle shifts linked to synthetic fixation. Such distinctions require special pages in the archive, pages written where time is most finely gridded. Anoxia provides that grid. When bottom waters go oxygen-poor or anoxic, burrowing stops and the seafloor stills. Fine laminae, sometimes seasonal, accumulate undisturbed. Winter and summer dusts, spring blooms pressed into paper-thin layers, storm pulses laid down like punctuation. In restricted basins and oxygen minimum zones, this quiet allows abrupt changes to record themselves with unusual fidelity. A sudden rise in nutrient supply appears as intensified organic-rich layers. A shift in carbon's isotopes is caught without being blended by worms. These laminated sequences, varves in lakes, sapropels in seas, the exquisite strata of fjords and marginal basins, become magnifying glasses for brief episodes. Deoxygenation also amplifies preservation. Organic matter that would otherwise be eaten is entombed. Delicate structures that would be churned are left intact. If an industrial phase carried with it an avalanche of fine soot, of microplastics sinking with biogenic debris, of metal-rich dusts, an anoxic basin would trap it with minimal reworking. The same is true for radionuclide peaks from atmospheric testing. They descend through the water column and fix themselves in narrow bands that can later be counted like rings. These layers, once buried and lifted into outcrop or drilled as cores, offer the closest approach to cinematic playback that geology allows. The deeper investigation, therefore, becomes a choreography of proxies and places. In ocean drilling programs, cores from multiple basins allow synchrony checks. Does the Delta 3C excursion in one ocean occur at the same stratigraphic moment as in another? Do Mercury peaks align across continents, or do they fade where volcanism did not reach? Do nitrogen isotopes in continental margins show the same directional shift when lakes inland register a comparable change? In laboratories, mass spectrometers parse isotope ratios to parts per thousand and parts per million, chromatographs separate complex organic mixtures into families and species, microscopes count fly ash spheres by the hundred amid coccoliths and foraminifera tests. The aim is not a single smoking gun, but a concordance, multiple, independent lines pointing to the same cause. Even absence has interpretive weight. Rare polymers may leave little that can be conclusively assigned after long burial, especially where temperatures climb or oxygen infiltrates. In such cases, attention turns more sharply to metals and isotopes, the indirect consequences of making and burning. Conversely, a basin rich in anthropogenic-looking organics, but poor in the expected metal companions, invites caution. Natural analogues can be deceptive, and contamination from drilling fluids or curation must be ruled out. The discipline polices itself by demanding replication. Another core, another lab, another proxy, a better resolved time series. Beyond the mechanics, a quiet philosophy guides the work. The planet is granted the first right of explanation. Volcanism, weathering, orbital packing, biotic feedbacks, these are prolific authors, and their signatures are known to be diverse. A prior industry, if it existed and left enough breath to be recorded, would need to write in a dialect that nature rarely uses. Fast, coordinated, globally coherent, and adorned with chemicals that life and lava struggle to produce at scale. That standard is not designed to be unreachable. It is designed to be honest about what the rocks can say. Thus, the fingerprint library is not a catalogue of certainty, but a set of lenses. Negative Delta 3C excursions, when paired with their rightful companions, sketch the tempo of carbon's perturbation. Shifts in Delta N whisper of fields and rivers taught to carry more than rain. Technofossils, reduced to residues, still tell stories in chemistry's prose. Metals, in their redistributed families, remember furnaces and mines. Plastics, long after form is gone, may linger as altered ghosts in shales. Hypothermals, interrogated with care, become training reels for what nature alone can stage. And anoxia, with its patient laminations, preserves the fleeting with an archivist's devotion. In these pages, a civilization's truest monument would be written, not in stone raised against the sky, but in stone pressed by the sea, where spectra and ratios take the place of pillars and gates, and where time, however stern, allows brief accelerations to be seen. The mystery deepens not with a revelation, but with a blur. The closer the record is examined, the more natural and industrial signatures converge, as if the planet had learned to imitate industry long before engines existed. Ratios that looked decisive begin to share a border. Peaks that seemed singular find company in older storms. What began as a search for artifacts within processes becomes a recognition that processes themselves can masquerade as artifacts. Indistinguishability arrives first through tempo. The hypothesis expects an industrial pulse to be swift, decades to centuries in onset, a blink of geologic time. Yet in laminated sediments, even the fastest natural jolts compress into thinness. A century can be spread across millimeters or pulled into a single, deceptively quiet layer. Age models carry uncertainties measured in decades or more. Reservoir effects and sediment mixing drift the timing of signals by just enough to counterfeit synchrony. A volcanic carbon release that unfolded over 1,000 years may, under the arithmetic of burial, be nearly indistinguishable from an industrial century. especially when the archive is no more resolved than seasonal stripes pressed into silt. The more faithfully the record captures brevity, the more ruthlessly it averages it. Chemistry complicates the boundary further. Plastics, relied upon as modernity's signature, do not survive as themselves. Heat and pressure decompose backbones into ensembles of smaller molecules. Oxygen and chlorine migrate. Catalysts and stabilizers reconfigure. Diagenesis, the long simmer of burial, can produce organics that resemble the altered residues of industry without any factory in the story at all. Aromatic clusters, halogen-bearing fragments, cross-linked carbon that sits on the spectrum toward kerogen. Even the absence of familiar compounds may prove nothing, except that temperature ran too high or oxygen arrived too early. In the end, a polymer's afterlife can read like a natural mystery written in synthetic ink. Metals, once promising as cartographers of human redistribution, reveal their own ambiguities. Large igneous provinces cast aerosols loaded with metals. Hydrothermal systems concentrate copper, nickel, chromium, and platinum group elements in unusual ways. Ashfall scatters glassy microbeads whose chemistry evolves with weathering. Mining and smelting leave distinctive spatial patterns and ratios, but those must be seen against a canvas that nature has already stained. Where fly ash spheres suggest combustion, explosive volcanism can deliver spheres as well, similar in form, different in composition, yet confusable under poor resolution. Rare earth patterns can reflect fertilizers and electronics, or phosphorite exposure and diagenetic sorting. The signal remains readable, but only with compound sentences, not a single element, but families and relationships, not a single basin, but a choir. Even isotopes, the careful scribes of planetary change, must be cross-examined. A negative excursion in delta 3C is a necessary component of any rapid carbon addition, but not a sufficient proof of industry. Methane hydrates, volcanic degassing of organic-rich sediments, and oxidation of peat and permafrost can draw the same downstroke. A reshaped nitrogen cycle in delta N can point toward fertilizer and wastewater, but also toward natural eutrophication, altered ocean circulation, or shifts in denitrification as climates warm and currents slacken. Each proxy argues, none concludes alone. Only their concordance, timing, direction, geometry across basins can approach a verdict, and even then, nature reserves the right to offer an alternative. The silence of technofossils sharpens the unease. If a prior industry once existed, where are its durable residues, its plastics turned to enigmas, its concretes reduced to strange cements, its fibers preserved as ghost threads? The geological answer remains austere. Preservation is rare, surfaces are temporary, and archives are selective. Subduction swallows oceanic crust. Erosion razors continents. Unconformities erase. Most urban footprints live on coastal plains, deltas, and river valleys, landscapes that migrate, drown, and efface. In 100 million years, vast industrial sprawl may be reduced to a handful of finely laminated basins, and those basins may be hard to find. What looks like absence may be the structure of the archive rather than the structure of history. A contemporary mirror deepens the caution. Even for the present, the effort to establish a formal, global stratigraphic boundary for human influence has met debate. What should count as the golden spike? Which site carries a signal most representative? How global and synchronous the markers must be. If naming a boundary for a living epoch is difficult when laboratories, satellites, and sensors monitor the world in real time, then diagnosing a chapter millions of years old demands a humility steeper still. The planet resists easy summaries. It prefers mosaics over declarations. There is also the problem of spatial aliasing, where local clarity is mistaken for global truth. A fjord may record an immaculate sequence of laminated muds bearing fly ash spheres, microplastic residues, and a tidy delta N deviation. A nearby shelf, battered by storms and worms, may blend the same decades into a statistical haze. Farther afield, a basin uninterrupted by anoxic episodes may carry only the carbon signal and none of the metallic or organic companions. Without a network of cores drawn from oceans and continents, lakes and shelves, the picture risks becoming a portrait made from a single eye. Synchrony tests, aligning isotope peaks across basins, matching mercury anomalies where volcanism is implicated, verifying that nitrogen shifts are not merely regional, become the discipline's discipline. As the investigation multiplies lines of evidence, a deeper fear emerges. What if an advanced civilization learned to live quietly, writing almost nothing geochemical into the page? If energy came from sources with minimal carbon footprints, geothermal, wind, or sunlight gathered without industrial chemistry on a planetary scale, then even prosperity might leave only modest edits. Electric arcs do not appear in clays. Efficient recycling narrows metal dispersal. Closed-loop chemistry keeps novel molecules inside walls that will not survive long. Intelligence, imagined as restraint rather than acceleration, approaches invisibility. The Earth would then sit with two possibilities in the same silence, that none came before, or that one did and passed like a careful wind. This possibility troubles the extrapolation outward. Astrobiology leans on the assumption that technology leaves atmospheric or surface hints visible from afar. Gases out of equilibrium, aerosols that nature rarely produces, light patterns from cities, waste heat glimmering in the infrared. If the Earth can host an industrial age whose clearest marks are subtle, local, and diagenetic, then telescopes may face a paradox. The civilizations easiest to find are those least skilled at living with their worlds. The quiet ones hide by success. Diagenetic mimicry adds further thorns. Under certain temperatures and pressures, organohalogens can originate from sedimentary reactions. Sulfurized organic matter can acquire halogens that were not part of initial deposition. Microbial communities can catalyze transformations that yield molecules with industrial analogs. Laboratory experiments show plausible pathways for creating compounds once thought diagnostic of manufacturing. Each new insight into the chemical creativity of burial is a small subtraction from the exclusivity of any one signal. Again, the response is not despair, but refinement. Longer analyte lists, tighter compound-specific isotope measurements, and an insistence on ensembles that nature struggles to assemble without invoking multiple, unlikely coincidences. Statistical reasoning therefore enters the chamber. The question shifts from is there a marker to what is the probability that this pattern, across proxies and basins, emerged without industry. Bayesian frameworks beckon, priors set by known natural variability, likelihoods drawn from training sets of hypothermals, anoxic events, and volcanic episodes, posteriors updated as each new proxy joins the chord. No single peak or ratio overcomes the null hypothesis. But a synchronized triad, a rapid delta-3 C drop paired with a global delta-N reorganization, and a geographically broad enrichment in metals aligned with mining ratios rather than ashes, begins to carve away the natural explanations. Add an organic suite featuring altered residues best explained by polymer ancestry, and the space of coincidence narrows again. The method accumulates constraint. The mystery remains allowed, but cornered. Yet the deepening is not only technical, it is existential. Intelligence is seen not as an exception to Earth's rules, but as one of their outcomes, an emergent metabolism that briefly accelerates fluxes and discovers new molecules. The shock lies in the thought that such a metabolism may be common in principle and still vanish in practice, leaving only geochemical size that blend with older weather. Civilizations, then, might be events like hypothermals, abrupt, consequential, recoverable. The crust would remember them as it remembers storms, by altered sandbars and shifted channels rather than by portraits. The search adapts. It abandons the hope for a single unmistakable artifact in deep time and turns to concerted multi-proxy choreography. It asks cores from oceans separated by continents to sing the same notes in the same order. It weights volcanic proxies, like mercury and sulfur, against mining patterns in metals. It pursues compound-specific isotope analyses to separate diagenetic cousins from manufactured ancestors. It develops models of how quickly human-like industry could write a global delta-3 C move, and compares those tempos to known natural packing. It teaches algorithms to discriminate subtle combinations, while insisting that algorithms never replace field sense. Context, stratigraphy, sedimentology, the physical story that holds the numbers together. And still an unease remains, productive and stern. The hypothesis does not promise discovery, It promises a way of listening worthy of the question. The deepening mystery is that the Earth may already contain the answer, and that the answer may be indistinguishable, at least in the present state of tools, from the background of a world that loves to run experiments on itself. This unease sharpens science. It compels cleaner extractions, better age models, finer laminations, new proxies, replicated cores. It asks for patience with ambiguity and courage with inference. If a prior civilization wrote its brief chapter, the most legible page may be narrow, laminated, and rare. It may lie in a basin where deoxygenation stilled the seafloor, in a core where delta 3C and delta N bent together, where metals settled in unfamiliar friendship, and where organic residues carry the shadow of polymers after the polymers are long gone. If no such page exists, the lesson is not that none came before, but that deep time is a poor keeper of delicate scripts. Either way, the search changes the reader. The Planet becomes a book that teaches how easily stories disappear, how loudly processes speak, and how intelligence, if it is to be known across ages, must learn to write in inks that stone can keep. The first theories stand on bedrock and fire. Nature, unaided, is prolific in its capacity to alter climate, oceans, and chemistry. Large igneous provinces pour basalt across provinces the size of nations and exhale CO2 and sulfur in pulses that buckle ecosystems. Submarine volcanism and hydrothermal venting shuffle metals into seawater, seasoning sediments with copper, nickel, chromium, and platinum group elements in patterns that follow magma more than machinery. Orbital cycles, eccentricity, obliquity, precession, pace ice sheets and monsoons. They modulate temperature and rain with a metronome set by celestial geometry. Clathrates, those icy cages of methane, can fail when warmed or unburied, sending light carbon upward with ferocious speed. Peatlands and permafrost, banks of ancient photosynthesis, can oxidize when climates tilt or shorelines shift, returning to the air what forests once kept. Biology, in its own ambitions, has authored revolutions. Oxygenation events that rusted the planet, algal blooms that turned seas breathless, microbial metabolisms that barter in sulfur and nitrogen and leave signatures in stone. These natural drivers form the null hypothesis, the scaffolding against which any industrial speculation must be braced. Each arrives with a partial fingerprint. Volcanism tends to accompany mercury enrichments in sediments, sulfur isotopic swings tied to atmospheric chemistry, and trace metal suites that correlate across ash layers and weathering pulses. Clathrate disruptions brand the carbon ledger with sharp negative excursions in delta 3C, often without the mercury that betrays magmas, and with recovery profiles shaped by ocean mixing and carbonate dissolution. Oxidation of organic-rich sediments, whether in floodplains or along marine margins, bears plant-wax isotopic echoes and sedimentological shifts in dust and grain size as landscapes reorganize. Orbital forcing leaves its quiet rhythms in carbonate cycles and lithologic alternations, a waltz that can be recognized when the layers are long and continuous. Having seated nature as the first author, the inquiry turns to industry as a hypothetical second. If a technological civilization had altered the Earth at scale, what specific hallmarks could distinguish its breadth from volcanism, biology, and weathering? The answer must move beyond any single proxy to ensembles that are improbable under natural scripts. One such ensemble begins with tempo. An industrial pulse is expected to be fast, decades to centuries in onset, perhaps a few centuries in plateau, then a tale of recovery governed by the planet's own packing. In sedimentary archives that capture annual or seasonal laminations, fjords, restricted basins, some lakes, such a pulse could present as a narrow band where multiple signals coincide. A sharp negative delta 3C shift sustained over tens to hundreds of laminae. A contemporaneous deviation in delta N indicating large, persistent inputs of fixed nitrogen. A dusting of spheroidal carbonaceous particles from high-temperature combustion. And subtle enrichments in metals scattered with spatial patterns unlike ashfall. Where resolution slackens, the signature compresses, but synchrony across basins remains testable. A near-simultaneous inflection in carbon and nitrogen across oceans far apart, too tight to be paced by orbital geometry or by the stagger of volcanic provinces. The second ensemble concerns chemistry that nature rarely scales. Synthetic organohalogens, molecules built with patterns of chlorine or fluorine attachment, uncommon in biogenic pathways, offer one such category. Some will not survive burial intact. Diagenesis is a long and creative chemist. Yet families of altered residues, recognizable by diagnostic fragments, unusual halogen ratios, or compound-specific isotope anomalies, could persist. Highly stable fluorinated architectures, even after partial breakdown, might seed sediments with organofluorine that exceeds natural baselines. In tandem with this, polymer additives, plasticizers, UV stabilizers, brominated retardants could leave descendant molecules that retain skeletons distinct enough to suggest ancestry. Alone, none is proof. Together, and aligned with other markers, they edge the probability away from igneous or microbial agency. Metals supply a third set of discriminants. Mining and smelting do not redistribute elements randomly. They alter ratios and co-occurrence patterns in ways tied to ore choice and industrial pathways. Platinum group elements, enriched by catalytic converter emissions, peak in roadside soils and can wash to estuaries and shelves. Their relative ratios differ from meteorite dust and from volcanic aerosols. Copper and chromium, released by industry, travel and settle with grain sizes and organic matter in patterns that diverge from hydrothermal sources. Rare earth elements, mobilized by electronics and magnets, might imprint subtle anomalies, flattened or spiked, normalized patterns distinct from those associated with phosphate deposition or igneous differentiation. Read across regions, a coherent, non-igneous metal fingerprint synchronized with isotopic disturbances would be an argument written in the periodic table's own script. A fourth set reaches into the nuclear age. Short-lived radionuclides, cesium-137, strontium-90, americium-241, plutonium-239, decay on human to geologic timescales that are brief. After millions of years, their gamma signatures will have vanished, but their daughters and their damage may remain. Localized anomalies in stable isotope ratios in glasses or minerals that trapped fission products. Excesses in uranium-235 relative to uranium-238, where plutonium once decayed. Radiation damage tracks frozen in vitrified materials or zircons near former test sites. These are faint possibilities. They require context and caution, for natural reactors have existed, as at Oklo, and cosmic rays draw etchings of their own. Yet paired with other markers, nuclear residues compose an alphabet seldom written by volcanoes. Fifth ensemble addresses nitrogen. Industrial fixation by the Haber-Bosch process reconfigures the nitrogen cycle from the land outward. In lakes and continental shelves, compound-specific analyses of chlorophyll derivatives and amino acids can capture delta-N changes linked to fertilizer use and wastewater inputs. In the open ocean, the balance between nitrogen fixation and denitrification may swing, shifting the isotopic composition of nitrate and the organic matter formed from it. A civilization-scale agricultural footprint could thus register not as a single deflection, but as a patterned, basin-to-basin reorganization of nitrogen flow. When that reorganization aligns temporally with carbon perturbations and metallic fingerprints, the ensemble begins to sing a single tune. With these ensembles proposed, the speculation broadens from signatures to scenarios. One scenario imagines a civilization that, like modern humanity, taps fossil carbon for energy. The expected mark is a rapid delta-3C decline, ocean acidification, warming, and deoxygenation, accompanied by metals and organics in patterns consistent with combustion, mining, and manufacturing. Another scenario envisions a technological species that drew primarily on non-fossil sources, geothermal, wind, hydro, solar gathered with minimal chemical externalities. Here the carbon and nitrogen signals would be muted, metal redistribution might be visible, but narrower, polymers might be rarer. The archive would then depend more on localized technofossils, rare laminated basins, and subtle metallurgical residues. A third scenario contemplates a civilization that achieves high energy densities via nuclear processes early in its arc. Its global carbon imprint could be small. Its marks, if any survive, would be regional, vitrified sands altered isotopic neighborhoods, strange glasses at limited sites. Each path leaves different odds of detection under deep time attrition. With scenarios comes the sober idea of brevity. Intelligence may be a flash, not a flame. An industrial phase could rise and resolve in centuries, leaving a thin line of commotion hard to find amid meters of tranquil mud. A planetary self-correction, by policy, collapse, or design, could curtail emissions before a global Delta 3C move grows large. The Earth system itself, swift in some respects, slow in others, might swallow much of the difference before it propagates everywhere at amplitude. The record would then honor the event faithfully in a few basins and forget it nearly everywhere else. In probabilities, this means that absence in most cores is not decisive. Presence in a very few, if clearly industrial, is transformative. The absence of an unambiguous ancient signal invites a wider speculation. The Great Silence, recast in stone. Perhaps technological civilizations, if they arise, trend toward efficiency that leaves little geochemical wake. Waste heat is minimized, atmospheric disequilibria are corrected as a matter of engineering hygiene, and novel molecules are contained in cycles that do not leak. The quietest, most enduring cultures may be those that write least in rock. If so, the universe's most common intelligence would be the hardest to see, both across interstellar distances and across eras. Detection would favor the unquiet, the extravagant, the wasteful, the short-lived. Astrobiological strategies built solely on pollution or disequilibrium might then be biased toward rarity. This is not a counsel of despair, but a refinement of aims. Theories converge on a practical doctrine. The search must privilege combinations, fast tempos, global synchronies, and chemical ensembles that nature struggles to assemble together. Bayesian frames become useful, where priors are taught by volcanism and hyperthermals, and posteriors are updated proxy by proxy. The likelihood that a given pattern is industrial decreases dramatically if mercury marches in lockstep with carbon, if metal ratios match ashfall, if nitrogen moves lag and lead in ways that echo known circulation changes. It increases when mercury is absent. Metals whisper of refineries rather than calderas. Nitrogen reorganizes landward and seaward together, and organics carry halogenated ghosts that burial alone is unlikely to design across oceans. Speculation also reaches forward. If future observers were to diagnose the present from a far century, which of modern signals would survive lucidly, the mid-20th century bomb peak is already a sharp stratigraphic razor for near-term layers. Spheroidal fly ash persists as glass and iron long after politics change. Platinum from converters seems sturdy. Microplastics will fragment and alter. Some fraction will likely carbonize and merge with kerogen-like phases, leaving molecular riddles. Delta 3C will remember the fossil pulse. Delta N will remember food. If these are the marks most legible to the future, they are also the templates against which the past can be scanned. At the edge of speculation lies humility. The planet is generous with rehearsals. It has manufactured black shales without factories, warmed oceans without engines, and rearranged elements without markets. Theories that assign industry must therefore carry more than novelty. They must carry necessity, the kind that remains after volcanic, microbial, and orbital scripts have been exhausted. In this rigor is a quiet reward. Even when the verdict is natural, the reading grows more articulate. Hyperthermals become sharper films. Anoxia gains dimensions. The choreography between land, sea, and air becomes clearer. The greatest speculation held lightly is that intelligence itself is a geologic agent that seeks to become less visible as it matures. Early stages flare, combustion, extraction, waste. Late stages refine, closed loops, minimal leakage, energy that does not write in stone. If that arc is real, the Earth's crust would carry a brief adolescent shout and then a long adult whisper. The search for predecessors is, in part, the search for such a whisper in unfamiliar places. In the most faithful laminations, in the most isolated anoxic vaults, in patterns too concerted and too quick to be a coincidence of magma and weather. Theories and speculations, then, do not promise discovery. They organize patience. They lay out what would count, where to look, and how to tell a chorus from a crowd. They ask the archive to show, if it can, a handful of pages where carbon and nitrogen lean together, where metals take unusual company, and where organics remember chemistry learned in furnaces rather than in cells. If those pages exist, they will be thin. If they do not, the Earth remains a self-sufficient storyteller. In either outcome, the method leaves a gift, a clearer understanding of how a world writes change and how a mind might someday learn to live without leaving a bruise. The work advances on decks and in darkness, on ships that idle above abyssal plains, and in laboratories where iron beams parse atoms like syllables. The mystery has asked for patience. The tools answer with precision. What survives in stone is subtle. What is looked for must therefore be many things at once. Fieldwork begins with cores, the planet's long cylindrical diaries. International drilling programs lower strings of pipe through kilometers of water to bite the seafloor, the North Atlantic's clay-gray pages, the equatorial Pacific's chalk, the hypoxic basins of the Santa Barbara Channel, Cariaco, and the Black Sea, where laminations stack like pressed seasons. Each core is logged immediately by multisensor arrays, density, magnetic susceptibility, natural gamma, so that hidden rhythms emerge before the mud has fully cooled. At the bench, an X-ray fluorescence core scanner runs along the split face, grain by grain, yielding profiles of iron, calcium, aluminum, silicon, and trace metals at millimeter resolution. Bands appear, dust pulses from continents, ash from distant eruptions, organic-rich layers where the sea forgot to breathe. These are the pages where a civilization's brief acceleration, if it occurred, would most likely have written. Time is the scaffold. Tephra layers serve as timestamps, glass shards geochemically fingerprinted and dated by argon clocks, tying one basin to another with the precision of a shared flare. Paleomagnetism adds its barcodes, polarity reversals recorded as iron-bearing minerals cooled or settled, allowing age models to lock onto the choreography of the planet's field. Where sequences are long and steady, astrochronology tunes the layers to celestial metronomes, 405,000-year beats of eccentricity, subtler waltzes of precession and obliquity, so that local pages align with global time. Bayesian age, depth models knit these constraints together, propagating uncertainty honestly, knowing that a century may be thinner than a fingernail. Chemistry plays the lead. Carbon's voice is measured first. Carbonate tests of foraminifera and the organic fraction of sediments are milled to powders. Isotope ratio mass spectrometers then weigh delta 3C to parts per thousand. A rapid excursion toward lighter values suggests a swift release of isotopically light carbon. Clumped isotope thermometry, reading the rare bonding of heavy isotopes within the same molecule, retrieves paleotemperatures from carbonates to gauge the fever that followed. On nearby benches, dissolved inorganic carbon in pore waters is sampled to see how burial is altering signals even as they are read. Nitrogen's reconfigured paths are traced next. Bulk delta N is measured in shelf muds and lake varves. Compound-specific analyses target amino acids and chlorophyll derivatives to separate sources and processes. Far offshore tiny shells, planktic foraminifera, hold nitrates memory as bound organic nitrogen. Their cleaning and analysis reconstruct the open ocean's delta N, showing whether fixation or denitrification dominated when climates leaned. A civilization-scale agriculture would leave a pattern coherent across river mouths and margins, lakes and shelves, a geometry of enrichment and depletion that biology alone rarely sustains on short timescales. Metals arrive as families rather than loners. Inductively coupled plasma mass spectrometry, ICP-MS, draws concentration curves for copper, chromium, nickel, and rare earths at the parts per billion level. Platinum group elements, sifted from sediments near coasts and estuaries, can reveal the whisper of catalytic converters long after roads are gone. Ratios matter. Volcanic aerosols tend to carry metals in company determined by magma chemistry and ash grain size. Mining and smelting scatter them along transport corridors, keyed to urban watersheds and atmospheric plumes. Microanalytical maps, micro-XOF mosaics across laminae, expose whether enrichments coincide with soot-rich layers or with ash shards, sharpening the difference between furnaces of basalt and furnaces of industry. Volcanism's signature is filtered explicitly. Mercury analyses, normalized to organic carbon, spike with large igneous provinces and explosive episodes. In parallel, Mercury isotope measurements can display odd mass-independent fractionations, diagnostic of atmospheric processing. If a carbon excursion rises without Mercury's company, suspicion tilts away from magma. Osmium isotopes add another discriminator. 187 Os 188 Os ratios carry the balance between mantle inputs and continental weathering, a lever that helps apportion causes during hypothermals. Strontium and neodymium isotopes trace dust sources and weathering intensity, revealing whether continents themselves were scoured harder when climates shifted. Organics are read as narratives rather than lists. Gas chromatography, mass spectrometry teases complex mixtures into identifiable peaks, plant waxes and algal lipids that carry climatic stories, polyaromatic hydrocarbons that speak of high-temperature combustion, occasional, ambiguous fragments consistent with altered polymer ancestry. Two-dimensional chromatography and pyrolysis, GC/MS, are brought to bear on samples whose macromolecular frameworks resist simple extraction, shales whose bitumen may hide reminders of a chemistry learned in reactors rather than in cells. Fourier transform infrared spectroscopy and Raman microscopy map microplastics in thin sections. Those same tools turn to deeper layers, search not for intact polymers, unlikely under heat, but for unusual functional groups and halogen signatures. Where fluorine is suspected, combustion ion chromatography measures total organofluorine, looking for excesses above natural baselines. Particles, the residue of fire, are counted by shape. Scanning electron microscopes survey laminae for spheroidal carbonaceous particles, smooth, glossy beads born in high-temperature, oxygen-poor combustion. Their abundance curves mirror the rise of coal and oil in the modern age. Their presence deep in time would demand explanation cautious and exacting. Volcanic spherules are similar in form, but differ in chemistry. Energy-dispersive X-ray spectra discriminate iron-rich industrial cenospheres from silica-rich ash glass, ensuring that resemblance does not seduce inference. Redox conditions, the oxygen state of ancient seas, are reconstructed with independent eyes. Iron speciation partitions reactive iron pools. When the ratio of highly reactive iron to total iron rises and the fraction bound to sulfide swells, anoxia and euxinia are implied. Molybdenum and uranium enrichments confirm and quantify their concentrations tied to the degree and duration of oxygen loss. Iodine to calcium ratios in carbonates capture near-surface oxygenation, while biomarkers like isorniaeretane, the pigment of green sulfur bacteria, testify to photic zone euxinia, the sunlit sea gone sulfidic. These proxies define the vaults where laminae are preserved and where brief events are recorded most faithfully. Experiments complement archives. Burial tests place modern polymers, polyethylene, PET, PVC, into anoxic and oxic sediments under controlled temperatures, retrieving them after months and years to trace chemical fates. The products map forward to compounds that might be found after geologic durations, cross-linked carbon residues, halogenated fragments, stubborn fluorinated ghosts. Technofossils are manufactured and broken on purpose, concrete cured and crushed, fly ash seeded into mini basins, metal filings scattered under known grain-size distributions, so that transport and deposition can be learned as dynamics rather than guessed as static pictures. These calibrations form a library of outcomes against which ambiguous ancient organics and metals can be compared. Clear residues are pursued with delicacy. Accelerator mass spectrometry detects vanishingly small quantities of long-lived radionuclides and their daughters. Fission track analysis in apatite and zircon distinguishes natural annealing histories from sudden, intense irradiation. Glasses formed in desert tests, trinitite today, ancient analogues if they existed, are examined for element partitioning and radiation damage, establishing what would be plausible to find and what would likely anneal away. The tools come with caveats. Natural reactors have left their own marks. Cosmic rays etch slowly everywhere. Context remains sovereign. Data, no longer scarce, demand choreography. Repositories accumulate time series from oceans and lakes, Loess and Pete. Machine learning sifts them not to replace interpretation, but to test for ensembles that recur under natural regimes and those that do not. Bayesian frameworks formalize what geologists have long practiced informally, priors shaped by hypothermals and anoxic events, likelihoods adjusted as mercury, metals, isotopes, and organics join the case, posteriors that quantify how far the null hypothesis has been eroded or restored by each new core. Outliers are examined twice, once for discovery, once for contamination. The gaze does not remain on Earth alone. Astronomers seek technosignatures in the skies of other worlds to validate the idea that technology can be read as atmosphere. Space telescopes now split the light of transiting exoplanets into spectra, measuring the fingerprints of water vapor, carbon dioxide, methane, and carbon monoxide. Claims of disequilibrium are tested against stellar noise and aerosols. Models account for star spots and hazes that mimic gases. Hypotheses propose species that biology rarely excretes at scale: nitrogen dioxide from combustion, chlorofluorocarbons from refrigeration, as search targets in favorable cases. Future observatories promise sharper views and broader wavelengths. Ground-based giants will join with higher resolution, peering at nearer, brighter worlds. Whether or not such gases are ever seen, the exercise feeds back. It forces clarity about which signatures are uniquely technological and which belong to planets at play. Earth observation tightens present-day baselines. Satellites that map nitrogen dioxide, sulfur dioxide, and methane draw contemporary plumes so that their settling into sediments can be modeled and checked. Carbon observatories refine fluxes across forests and cities. Their inversions constrain how quickly a rapid pulse would echo into the ocean and the carbonate system. These instruments, built for policy and climate, double as time machines. They show how a brief industrial era translates into the proxies that rock will keep. Standards keep rigor from fraying. Contamination control is severe where plastics are counted. Clean rooms, cotton lab coats, procedural blanks, airborne fiber traps. Drilling fluids are dyed and chemically tagged so that any intrusion into cores is recognized and removed from consideration. Cross-lab intercomparisons ensure that mercury spikes are not artifacts of digestion protocols and that delta-N differences survive differences in combustion systems. Blind samples circulate. Results that fail to replicate are set aside rather than fitted. The testing in all of this is ongoing by design. New cores from old places, another transect across a margin, a deeper bore into a laminated basin, arrive to check whether a pattern holds or fades under better resolution. Lakes newly recognized as varved, quiet, annually layered waters are added to the network, their thin archives expanding the geographic web for synchrony tests. Old samples are reanalyzed with new tools: compound-specific isotopes where bulk once sufficed, mercury isotopes where only concentrations were known, fluorine screens where halogens were never sought. The archive does not change, the instruments do. Behind the analytics, a simple strategy persists. To distinguish a technological event from nature's rich repertoire, science seeks consonance, rapidity legible beyond noise, global synchrony across unlike basins, chemical ensembles that ask too much of volcanoes and weathering alone. It looks for the company of signals, a negative delta 3C excursion arriving with a coherent reorganization of delta N, with metals distributed in mining patterns rather than igneous families, with organic residues that carry halogen logics foreign to cells. It checks that volcanism's proxies are absent when magma is accused, and present when magma is likely. It verifies that the finest laminae sing the same notes as the coarser pages nearby. If the answer is silence, the tools will have still done their work. They will have sharpened the picture of hypothermals and anoxic worlds, refined the tempos of weathering and recovery, and taught how quickly seas can forget and remember breath. If an anomalous chord is eventually found, thin, global, concerted, the same tools will carry the weight of proof. The planet has offered a record of processes rather than artifacts. The instruments, in response, have learned to read processes as biographies. In their patient calibration lies the only honest way forward: to keep sampling, keep measuring, keep asking multiple questions of the same thin layer until it either confesses an artifice or rests securely as nature's own design. In a quiet room, under the softened glare of lab lights, a single core lies open like a slender biography. Its varnished face gleams with subtle bands, dawn-dark, bone-pale, ash-gray, each a breath, each a season, each a century pressed to a thickness thinner than a fingernail. Instruments crowd the bench, but the scene carries a hush older than tools. It is the hush of stone when it is asked a careful question. The Silurian Hypothesis has not tried to resurrect a lost metropolis or name a vanished people. It has asked something sterner, how intelligence, if it has happened before, would be remembered by a planet that prefers to keep processes rather than monuments. The query changes the scale of wonder. Civilizations, in this light, are not primarily architects of towers, but editors of cycles. They are accelerations written into carbon and nitrogen, redistributions of metals, brief inventions of molecules that nature rarely attempts. Measured against the oceanic patience of geology, such accelerations are flickers, yet flickers can burn images onto film. The question is whether the film survives. Time, which Einstein allowed to bend with gravity and splice with space, behaves differently inside a rock. In the geometry of relativity, now is a local custom. In stratigraphy, now is a page assembled from a million drifting grains. Entropy leans forward everywhere. Information, as those grains arrange themselves, is kept or lost according to rules indifferent to drama. Hawking once followed the arrow to horizons no signal could cross and asked what it meant for information to be swallowed and diffused. The Earth, less absolute but equally relentless, offers a domestic version of that paradox. Memory is not refused, it is thinned, needed, reworked. A metropolis may end as centimeters of altered isotope ratios and a lace of unfamiliar residues. The planet does not erase with malice, it edits for concision. If intelligence is approached as geochemistry, humility follows like a tide. A species can move mountains and bring glow to midnight, yet still be averaged into clay. The planet fills its shelves with storms older than agriculture and fevers older than engines. It has staged anoxic seas under green suns and warmed itself with breaths that never passed through lungs. It can counterfeit some of the very signatures an industry would leave behind. The lesson is not futility, it is scale. Knowledge gathered by telescopes and particle colliders must be matched with an ethics of proportion. Actions that feel planetary at the level of a life are small disturbances at the level of a column of mud. They will be remembered, if at all, by concordances, by ensembles of signals that rhyme across oceans. The mystery, then, reaches outward as much as backward. The search for prior industry inside Earth's rocks calibrates the search for other minds in other skis. If this world, saturated with sensing, struggles to distinguish an industrial century from a swift geologic fever, then telescopes peering across light years will be forgiven for hesitating before a single spectral line. Technosignatures must be ensembles there as well. Gases out of equilibrium, gathered with aerosols unlikely in nature, light curves whispering of cities, waste heat out of phase with seasons. The Silurian lens insists on restraint in inference and courage in patience. It teaches that the cosmos may reward those who ask multiple questions at once and punish those who fall in love with solitary anomalies. Even without a confession from stone, the thought experiment alters self-understanding. It suggests that intelligence is not only a property of minds, but a planetary event, an emergent metabolism that accelerates fluxes, invents chemicals, and then contends with the consequences of its speed. In that metabolism, there are phases. Early phases flare, carbon unbanked, metals scattered, novel molecules escaping their intended circuits. Later phases, if wisdom follows knowledge, grow quiet, closed loops, minimal leakage, energy that does not force the carbon ledger to lurch. The arc from flare to hush is not guaranteed, but if civilizations endure, their geochemical handwriting may become subtler until their stories are legible only to instruments designed with foreknowledge of what to seek. The irony is tender. The most successful cultures may become nearly invisible to the very sciences they would have inspired. The possibility that none came before remains consistent with the archive. Uniqueness retains dignity. Nothing in physics forbids a singular event. Nothing in probability demands companions. Yet the possibility that others did arise and passed, like a disciplined whisper, has an equal poise. Between those poles hangs an ethic. If the rock keeps only the most deliberate edits, those made in concert across basins, those fast enough to register and coherent enough to distinguish, then the choice of how strongly to write becomes a moral choice as well as a technical one. An age can be designed as a bruise or as a trace. This reframing echoes beyond geology. It leans into policy and culture without speaking their names. If the most enduring monuments are cycles gently kept in balance, then stewardship becomes an art of remaining legible to selves while growing illegible to stone. The measure of advancement is not the height of skyline or the reach of power grid, but the degree to which a species can meet its needs while leaving carbon and nitrogen close to their long arcs and confining novel chemistries within loops that do not leak into oceans and bone. The archive is not a judge, but it is a witness. It rewards restraint with silence. Silence, however, is not emptiness. In cores drawn from deoxygenated basins, pages accumulate with the fidelity of a diary. If a brief industrial event lies buried in some distant epoch, its clearest trace may be there, thin, dark, speaking in ratios. The thought that such a page could exist, and that discovering it would alter the story of intelligence from singular to cyclic, compels a broader patience. The meaning would not be triumphalist. It would not make the present smaller. It would make the present continuous with a deeper pattern. Worlds that can host minds sometimes do, and minds sometimes learn to change worlds, and worlds always answer with physics. The dignity of culture would remain local and whole, only its category would shift from exception to recurrence. The unanswered questions do not weaken the inquiry, they animate it. What is the minimum footprint of a technological phase visible after 10 million years? How quickly must a carbon pulse arrive to be distinguished from the breath of magma, which molecular ghosts of polymers can outlast burial without masquerading as products of diagenesis? How do mining signatures scatter differently from volcanic aerosols once currents and storms handle them? What is the shortest-lived but still global chord that stratigraphy can hear? Each question begets a method. Cleaner extractions, compound-specific isotopes, cross-basin synchrony checks, training sets built from nature's own extremes. In seeking a prior civilization, science becomes better at reading this one, and better at guarding the only world known to carry thinking seas and articulate stone. The narrative, in the end, returns to the table where the core rests. Carbon and nitrogen curves have been drawn, soot counted, metals mapped, polymers searched for and where found, examined under suspicion. The page does not insist on an answer. It offers a range and a cadence. The cadence is the planet's, long unrest punctuated by swift events, slow recoveries paced by carbonate and weathering, breezes that become rivers that become layers. The range is the species, the capacity to err at scale, to learn at pace, to fold knowledge back into restraint. In that interplay resides meaning. Intelligence, if it endures, is not merely the ability to build engines and instruments. It is the willingness to hear what stone is saying about time and to compose a life inside those measures. Elsewhere, telescopes assemble. Mirrors cool in shadows at Lagrange points. Spectrographs wait for transits. Algorithms practice on simulated skis. They will report soon and then again, and then for as long as patience holds. A spectrum may brighten with gases that augur industry. It may remain austere, the mark of weather and volcanism alone. Either outcome instructs. A positive teaches how minds alter air. A negative, repeated across thousands of worlds, teaches how rare a certain kind of impatience may be. The Silurian Hypothesis, born in a paper about Earth, becomes a discipline for the sky. The last image is deliberately plain. No vanished avenue under jungle, no statue wrested from silt. A drill turns, a core rises, a thin, dark lamina is laid on a cold table. If the page contains a confession, it will be a confession in chemistry, not in script. If it does not, it will be a lesson in the grace of natural volatility. In both cases, the task is the same: to read, to learn, to choose how strongly to write. The planet will continue to average and to edit. It will abide tides and winters, fevers and calms, indifferent to pride, faithful to physics. Intelligence, if it wishes to be more than an instant, must learn how to become a long sentence in such a book, measured, coherent, legible to those who come later, or perhaps, mercifully, not legible at all. The stone keeps the last word. The work is to decide which word it keeps.